Alright, so we just put together an equation based off some basic observations of gas, and we called it the ideal gas equation, or PV equals nRT. And for the most part, the equation is pretty intuitive, but I remember that when I was learning it for the first time, the part that confused me the most was this constant value, R. So that's what I want to try to clear up for you now. So for starters, R is a constant. And what that means is that as the rest of the variables change with whatever situation we're looking at, the R value is going to stay the same. So let me show you what I'm talking about. Let's isolate R. So when we divide both sides by the moles and the temperature, we're going to get R is equal to PV over NT, which means that for any ideal gas, if you multiply the pressure and the volume and you divide that product by the number of moles and by the temperature in the system, you're going to get the same number. Again, for any ideal gas, you'll always get the value R. So I'm going to show you how this works, but first I need to make sure that we're on the same page about a couple different things. First, I need you to know that when I say STP, I mean standard temperature and pressure, and the standard temperature is 273 Kelvin, which is the same thing as 0 degrees Celsius, and the standard pressure is 1 atmosphere. So standard temperature and pressure is just kind of a nice theoretical condition that we can perform kind of situational experiments with. And so the second thing that I need to clarify is that we find experimentally that for any ideal gas, 1 mole of gas takes up a volume of approximately 22.4 liters. And we're going to use these conditions to find the ideal gas constant. So let's start with R equals PV over NT. And for our conditions, we're going to talk about 1 mole at standard temperature and pressure. So for our pressure, we have 1 atmosphere, and then we have 1 mole. And we know that 1 mole is 22.4 liters, so that's our volume. And again, at standard temperature and pressure, we're talking about 273 Kelvin. And this should equal R. So if we solve this out, our 1's are going to cancel, and we really just need to divide 22.4 by 273. And that's going to give us 0.0821. And then our units are going to be atmospheres times liters, so atmospheres times liters, divided by moles times Kelvin. So the constant R is equal to 0.0821 atmospheres times liters divided by moles Kelvin. So this is the ideal gas constant that's going to be the same for all ideal gases as long as we're dealing with pressure in atmospheres and volume in liters. And it's probably the one most often used in general chemistry. But, and I mentioned this earlier, sometimes we deal with pressure in a unit called a Pascal. And we deal with volume in cubic meters. And we use both of these because they're both based off of SI units. And so we might have another value for R, which looks like this. We're still going to start with R equals PV over NT. And we're still going to use standard temperature and pressure, but for our standard pressure, instead of using atmospheres, we're going to use pascals. And so 1 atmosphere is equal to 101,325 pascals. So 101,325 pascals is going to be our pressure. And we're still going to use 1 mole of gas. But instead of measuring the volume of 1 mole in liters, instead of saying that it's equal to 22.4 liters, I want to do it in cubic meters because that's another SI unit. So 1 cubic meter is equal to 1,000 liters. And this means that if we take 22.4 liters and we do a dimensional analysis, we're going to get 0.0224 meters cubed. And so that's the value that we're going to use in our formula because we're still talking about 1 mole, so 0.0224. And then last but not least, we're still talking about standard temperature and pressure, which in Kelvin the temperature would be 273. So we have our pressure, we have our volume, we have our moles, and we have our temperature. And so if we run this through a dimensional analysis to see if we can cancel any units, we would start with 101,325 pascals. But keep in mind that a pascal is the same thing as saying a Newton per meter squared because it's a SI unit of pressure. So we'd have 101,000 325 newtons per meter squared. And then we would take our volume, and that's 0.0224 meters cubed, and so we would put that in there, and our meters, most of our meters would cancel, 2 of the meters on top and 2 of the meters on the bottom, leaving us with just a meter on top. And then we would add in a division by 1 mole, because we're dividing by 1 mole, and we'll put that on the bottom, and then we'll finish it off by putting 273 Kelvin on the bottom. And so if we simplify this down, we'd say that 101,325 times 0.0224 divided by 273, and that would give us a value of R equals 8.314 Newton meters per mole Kelvin. And we could simplify the units just a tick more, because Newton meters are the same thing as joules. So we could just insert a joule, and we'd have joules per mole Kelvin. Now, to be sure, the constants look different here, but keep in mind that the only thing changing are the units. The values here are still the same, and it's always the same for any ideal gas. So for any ideal gas system, the product of the pressure and the volume divided by the number of moles and the temperature is equal to R, which might look like 8.21 times 10 to the negative 2 atmosphere liters per mole Kelvin, or it might look like 8.314 joules per mole Kelvin. But again, this is the same value. So think about what this means. If R is constant, then R is equal to PV over NT for the initial state of a gas, so for the initial state of a gas, but R is also equal to PV over NT for the final state of a gas, so for a final state of gas. And this is true because PV over NT always equals R for any ideal gas. And so what we're really saying here is that the initial PV over NT is equal to the final PV over NT, which opens up all sorts of neat kind of predictive possibilities, say if we were to change one of the variables. And we're going to explore these possibilities in the next few videos.